Hello, and welcome to my channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. In inferential statistics, we don't have all the data from a population or process, so we perform statistical tests on a sample or samples of data. The two main methods of inferential statistics are hypothesis testing and confidence intervals. And there are four statistical concepts which are central to inferential statistics. P, the p-value, alpha, the level of significance, test statistic, and critical value. In the book, there are individual articles on each of these four concepts, and I plan to do individual videos on all of them as well. This is the second video. There will also be a video on how these four concepts interrelate and work together, which is something I think is lacking in most books and videos. As usual, in the book and in these videos, we'll start with a list of keys to understanding, or KTUs, and then we'll go into detailed explanations of each key. The first key to understanding is, in inferential statistics, P is the probability of an alpha, false positive, error. The second KTU is, alpha is the highest value of P that we are willing to tolerate and still say that a difference, change, or effect observed in the sample is statistically significant. The third key to understanding is, alpha is a cumulative probability represented as an area under the curve at one or both tails of a probability distribution. P is also a cumulative probability. KTU number 4 states, in hypothesis testing, if P is less than or equal to alpha, reject the null hypothesis. If P is greater than alpha, fail to reject, some say accept, the null hypothesis. And the final key to understanding, number 5, says, alpha defines the critical values of test statistics, such as z, t, f, or chi-square. The critical value or values, in turn, define the confidence interval. And here on one page are the 5 keys to understanding the concept of alpha, the significance level. You may want to pause the video at this point and read them all together. Let's now begin with our detailed explanation of each key to understanding. KTU number 1 says, in inferential statistics, P is the probability of an alpha error. Now, in inferential statistics, we don't have all the data for a population or process. The population is too big, or an ongoing process is always producing new data. So we use data from a sample to calculate a statistical property, say the sample mean. And we use this as an estimate or inference of the corresponding property in the population or process, the population or process mean. Now, being an estimate, there is a risk of error. And one type of error is the alpha error, also known as the false positive error. P is the probability of an alpha error. Alpha error is also known as false positive or type 1 error or error of the first kind. Its opposite is a beta error or false negative. An alpha error is the error of seeing something that is not there. It is the error of concluding that there is something, a difference, change, or effect, when in reality there is not. In hypothesis testing, an alpha error is the error of rejecting the null hypothesis when the null hypothesis is true. The null hypothesis states that there is no difference, change, or effect. If the null hypothesis is true, then there is no difference, no change, or no effect. In that case, if our test concludes that there is a difference, change, or effect, then that would be an error, a false positive, an alpha error. For example, in blood testing, a positive conclusion means that there is a disease present. If there is in fact not, then the conclusion of positive is false. So we would have a false positive that is an alpha error. The probability of an alpha error is P, which is one of our four central concepts in inferential statistics. Key to understanding number 2 says, alpha is the highest value of P that we are willing to tolerate and still say that a difference, change, or effect observed in the sample is statistically significant. First of all, this says that alpha is a value of P. And since P is the probability of an alpha error, alpha is a particular value of the probability of an alpha error. KTU number 2 goes on to say that alpha is a clip level, a boundary level. It defines the boundary between those values of P which indicate that there is a statistically significant difference, change, or effect from those values of P which indicate that there is not a statistically significant difference, change, or effect. For example, if alpha is 5% and P is calculated to be 8%, then P is greater than alpha. So the probability of an alpha error, P, is higher than what we said we were willing to tolerate, alpha. So we conclude from the test that any difference, change, or effect observed in the sample data is not statistically significant. On the other hand, if P is 4%, then P is less than or equal to alpha. The probability of an alpha error is less than what we said we would tolerate, so we conclude that the difference, change, or effect is statistically significant. You can see why alpha is called the significance level, or the level of significance. It is the level of P which defines the difference between a result that is statistically significant from one that is not. We said that alpha is the highest level of P which we are willing to tolerate. That implies that we have a say in the value of alpha. And indeed, the person performing the statistical analysis selects the value for alpha. This must be done before the sample of data is collected. The reason is that if we have a peek at the data first, that might influence our choice of alpha, and that would compromise the integrity of the test. When thinking about a value for alpha, it may be more natural to think about a level of confidence, which is the opposite of the level of significance. For example, if we want to be 95% confident of avoiding an alpha error, then we would select alpha equals 5%. And this is the value of alpha most commonly selected. Since we get to select the value for alpha, why don't we always select something very small, like 0.0001? It's because there is a trade-off between alpha error and other kinds of error. For example, if we are willing to tolerate only a very low probability of alpha error, then we must live with a higher probability of beta error. Likewise, a lower value selected for alpha results in a higher margin of error. The only cure is to increase the sample size. The trade-offs still remain, but a larger sample size will reduce the probability of all these types of errors. Key to understanding number 3 states, alpha is a cumulative probability represented as an area under the curve at one or both tails of a probability distribution. P is also a cumulative probability. So alpha and P are both cumulative probabilities. That is, they are probabilities of not just a single value, but probabilities of a range of values. They are depicted as areas under the curve of a test statistic, such as z, t, f, or chi-square. In this illustration, alpha equals 5%. If the test is two-tailed, then we plot alpha divided by 2 as two shaded areas, one under each tail of the distribution of a test statistic. If the test were one-tailed, as in the diagram for P at the bottom of the page, we would plot the whole 5% under the appropriate tail. Tails are addressed in more detail in the book article and in the video on the alternative hypothesis. The inferential statistical test uses the sample data to calculate a value of the test statistic. Here, z has been calculated to be 1.2. We plot this value of z as a point value on the horizontal z-axis. P then is the cumulative probability of the range of values starting with z equals 1.2 and continuing rightward through z equals positive infinity. Our fourth key to understanding states, in hypothesis testing, if p is less than or equal to alpha, reject the null hypothesis. If p is greater than alpha, accept, that is, fail to reject the null hypothesis. Remember, p is the probability of an alpha error, and alpha is the maximum value of p that we will tolerate and still call the results statistically significant. And the null hypothesis states that any difference, change, or effect observed in the sample data is not statistically significant. Let's first deal with the case where p is less than or equal to alpha. Then the probability of an alpha error, p, is less than or equal to the level of significance alpha. We are willing to tolerate that level of p and still call the results statistically significant. So we conclude that any difference, change, or effect observed in the sample data is statistically significant. Now that contradicts the null hypothesis, which states that there is no statistically significant difference, change, or effect. Since the results of our test contradict the null hypothesis, we reject the null hypothesis. Conversely, if p is greater than alpha, then the probability of an alpha error is greater than the level of significance. The probability of an alpha error is too much for us to tolerate. So we conclude that any difference, change, or effect observed in the sample data is not statistically significant. This affirms the null hypothesis, which states that there is no statistically significant difference, change, or effect. So we failed to reject, some say we accept, the null hypothesis. There are separate articles in the book and separate videos on the concepts of hypothesis testing, null hypothesis, reject the null hypothesis, and fail to reject the null hypothesis. Key to understanding number 5 says, alpha defines the critical values of test statistics such as z, t, f, or chi-square, and the critical value or values in turn define the confidence interval. First, let's illustrate how alpha defines the critical value. The person performing the analysis selects the value for alpha, 5%, in these two concept flow diagrams. If the test is to be one-tailed, that is right-tailed or left-tailed, then the full 5% cumulative probability is plotted as one shaded area under one tail of the curve of the probability distribution of a test statistic, z in this example. Since z is a test statistic, we can calculate or look up in a table the value of z, which forms the boundary of a 5% cumulative probability area under one tail. For a right-tailed test, z equals 1.645. For a left-tailed test, it would be negative 1.645. These are critical values. The second concept flow diagram shows a two-tailed test. Alpha is divided in half, and 2.5% is placed under each tail. This gives us critical values of negative 1.96 and positive 1.96. For more on tails of tests, see the book article or the video on alternative hypothesis. This concept flow diagram shows how we complete the connection between alpha and a confidence interval. A sample of data is collected. In this example, we collect heights in units of centimeters. A sample statistic is calculated. In this case, we are interested in the sample mean, symbolized by x with a bar on top. It is calculated to be 175 centimeters in this example. To make use of the critical values in the real world, we need to convert the test statistic values into real-world units. There are different formulas for doing this for different test statistics and different tests. Here, the one for Z is relatively simple. Converting critical values into real-world units gives us the upper and lower confidence limits of 170 and 180 centimeters in this example. These define the confidence interval. There are separate book articles, and there are or will be separate videos for the concepts of critical value and confidence intervals. That concludes our discussion of the concept of alpha, the significance level. As I said earlier, this is the second of 5 related videos on 4 central concepts in inferential statistics and how they work together. Depending on when you view this video, they either are or will be available on my YouTube channel. You can view the status of videos completed and planned on the videos page of the book's website, statisticsfromatozee.com/videos. Okay, that's it for a clarification of this confusing concept. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concepts in the book, if folks like you tell me that more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website, statisticsfromatozee.com, has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatozee.com/blog. I've got some things there that hopefully you will find interesting, like a statistics tip of the week series, as well as posts showing that you are not alone if you are confused by statistics. I'll also be posting on the Facebook page, Statistics from A to Z, and on Twitter as @StatsA to Z. Till next time, I'm looking forward to communicating.